Okay, so let's revisit example 4.7 from the text, which is shown here. So the steering linkage for the front wheel of an off-road vehicle is what's shown here. And you can see that in order to steer the vehicle, you apply this force F, and the direction of the force is given here in terms of the components, 8, 9, and 12. And the rotation is about this line A, right? And the force is exerted obviously not on a line, off the line in order to create a moment, and it's exerted at this point A, which is located here at 160 minus 20 and 100 millimeters. So the question asks that we determine what magnitude of force is required in order to produce a moment about that line A, so the rotation line there, of 10 Newton meters. And in part A, the line is in the YZ plane, but it's rotated 10 degrees away from the Z-axis. And then in part B, the line is, so the line A is coincident with the Z-axis. So go ahead and try that and come back and we'll go through the solution together. Okay, so just to sort of go through the solution process, let's think about the things that we know. So we know this point 0, which we're going to define as the origin, lies on line A, and then we also know the coordinates of point A here. So we can determine the position vector ROA, which goes from line A, so from a point on line A to the location where the force is actually applied. The other two things we know from the problem statement are the direction of the force, right? So we know these components, so we can define a unit vector that tells us the direction the force is pointing, and we know the direction of line A because we know its angle relative to the z-axis. So the force vector then is going to be the magnitude of the force, which we don't know, multiplied by this unit vector, and then the vector moment produced by this force about point O is just the cross product of the position vector ROA and that force. And then if I want the magnitude of the moment produced around this line, I just have to take the dot product, so the projection of that moment produced around point O onto line A, right? So that is the dot product of MO with the unit vector UA. And so those are the set of equations, and then we add in the requirement that the magnitude of that moment, MA, must be 10 Newton meters, and we have a complete equation set. All right, so with that, then we'll go ahead and open up EES and try to solve this using vectors. So I am going to enter an angle here. That 10 degrees is an angle. It's going to be in degrees, so I better use the dollar unit system directive to specify that I'm going to use degrees. Let's see, I know the coordinates O and A, so I'll go ahead and enter them. O is just 0, 0, 0, and A is vector assign 160 minus 20 and 100. I know the angle, so I know the unit vector for line A, which I'm going to call UA. The angle relative to the z-axis is 10 degrees, so UA then is vector assign 0, and then the y component is the sine of theta z, and the x component is, or the z component is the cosine of theta z. And then I also know the unit vector that defines the direction of the force. So let's see, it's got components in the x direction minus 8, in the y direction minus 12, and in the z direction 9. I think that's right, yeah. And that's not a unit vector, it's only a unit vector if I then divide that by the magnitude, which is, I guess, minus 8 squared plus minus 12 squared plus 9 squared. So that's my unit vector use of f. I can go ahead and define the position vector ROA. That's just A minus O. And at this point then, I can try to enter this complete set of equations. So I guess this would be 3 equations along with the specification that MA must be 10 Newton meters, and try to solve. If I try to do that, it's likely that I'll make a mistake and not know where the mistake is, and it's possible that E's won't converge. So a much better approach is to enter a guess value for the magnitude of the force, and then enter each of the equations sequentially, solving as we go, so that I'm sure I haven't introduced any errors. And then finally update our guess values, comment out the guess value of F, and require that MA must be 10 Newton meters. So that's what I'm going to do here. It leads to much less frustration. So my guess value for the force is that the force is 10 newtons. If the force is 10 newtons, then I can calculate the vector force. It's just the magnitude of the force times that unit vector. I can check it, make sure it all looks okay. I can determine the moment that this force produces about 0.0. So that's just vector cross ROA with F. So this is MO. And then finally, I can determine the projection of this moment vector onto line A. And that's just the dot product. So vector dot of MO and UA. And if I solve, I see that the magnitude of the moment on line A is minus 1434 Newton millimeters, or minus 1.434 Newton meters. And that's what I get for the assumed value of 10 Newton. So a couple things to see here. One is that obviously if I want 10 Newton meters of moment, I need a bigger force than 10 newtons. Right? I got to jack that force up to get that moment. And the other thing is that the moment that I'm getting for this positive force is negative, and that should make sense to you given that the line A is directed upwards, and so that force is trying to rotate me clockwise around that line, and that's a negative direction. All right, so at this point I have a working solution. I could just sit here and increase F until I get to I guess in this case it'll be minus 10 Newton meters of moment, or I can let E's do that for me. So that's what I'm going to do. I'm going to update my guesses. So calculate menu here, update guesses. I'm going to comment out my assumed value of F. Of course, at this point I don't have enough equations, so I got to add an equation, and the equation that I'm going to add is that the magnitude of the moment projected onto line A must be minus 10 Newton meters, and I got to convert that to Newton millimeters given the unit system that I'm working in. And at this point, if I solve, EES has no trouble identifying that the force that would give me that moment is 69.75 newtons, and that agrees with the results in the text. So at this point, it's also kind of nice to look at this in a 3D vector plot. So I'm going to plot the position vector and the force and the moment, and then I'd also like to plot the vector moment in the direction defined by line A. So that vector moment MA is just the magnitude that I just specified, 10 Newton meters, multiplied by the unit vector that defines that line, so UA. So I'm going to calculate that. Just like in our previous problem, these moments have magnitudes that are so large that if I plot them with the position vectors and the forces, you wouldn't see the position vector and the forces. So I'm going to scale them down so that they all show up in one plot. And that, for me, is just going to be dividing them by 100. And then I'll use the $vector plot directive. I'll name my plot vectors. I'm going to plot the position vector ROA. Of course, that's going to start at line O, or point O. And I'll make that black. I'm going to plot the force F. That'll start at point A, because that's where it's applied. I'll make that red. And then I'll plot my two scaled moments. So I'll make these purple, and because they're both applied at point O, I will start them both at point O. And here's my vector plot, and you can see that MO is larger than MA, I guess, obviously, and then when I project MO onto line A, I get this MA moment vector. And then in part B it says solve it again, but this time assuming that the rotation axis is coincident with the z-axis, and that's very easy, right? All I have to do then is go in and change my my angle theta z from 10 degrees to 0 degrees, and when I solve, I get 81.73 newtons is now required, which again agrees with the text. And one of the nice things is about using the dollar vector plot directive is that every time I solve, my vector plot updates and refreshes. So I can go look at it now, and you can see, yeah, the MA scaled is in the z direction, which is exactly what I would have expected. And MA scaled has the same magnitude as it did before, but because it's in this new direction, MO scaled, which is the scaled moment around point O, has to be a little bit bigger. So some other things that we can do, just because we have this all sort of coded up in a computer program, is we can look at what the relationship is between the force that's required and the angle of this rotation axis line A. And one way to do that is I make a parametric table that contains theta z, the variable theta z, and the magnitude of the force. And maybe I'll vary this, I don't know, from minus 30 degrees to 90 degrees, and we'll solve the table. And you can see that, yeah, there is an optimal angle of rotation in the YZ plane to have this angle of rotation, and it's about 40 or 50 degrees or something like that, and that gives you the smallest force required to produce a steering moment. And of course, the other thing I can do if I want to get a more exact answer is use the optimization algorithm. So I'll go ahead and min-max here from the calculate menu. I'll set this up so that I am minimizing mag f by varying the independent variable theta z, and if I set some reasonable bounds here and hit OK, I find that the lowest magnitude of the force would be 55.6 newtons, and that's going to occur if I set my rotation angle to 47.12 degrees.